Hello, I'm MidiaYousefi and I will present our work on real-time speaker counting for cocktail party scenario. I hope you enjoy this presentation, and if you have any question regarding the content of this presentation or the details of the paper, please do not hesitate to contact me by email. So let's get started. I'll start by sharing my slides. So our work focuses on real-time speaker counting in a cocktail party scenario using attention-guided convolutional neural network. I did this work during my PhD with Dr. John Hansen in CRS's UT Dallas. So in this presentation, I'll go through the problem formulation and our motivation for solving this problem. And I'll also briefly mention some of the existing challenges and past approaches. In the next section, I will propose our solution for this problem, which is attention-guided CNN for frame-level source counting. And then finally, I will present our results and experiment, and I'll share with you some of the conclusions that we derived based on the experiments. As we know, spontaneous conversations, such as meetings or debates, they tend to contain a lot of overlapping speech. And these audio segments tend to degrade the performance of many speech technology applications, such as ASR, digital hearing aids, and mobile voice telecommunications. However, human auditory system is equipped to selectively attend, recognize, and extract meaningful information from complex auditory signals in noisy environment. But the machines don't have this ability yet, at least to an extent that it's desirable. Therefore, it is important to develop solutions that are able to handle overlap speech. The first step in processing overlapping speech is to estimate the number of active speakers within that segment. There are mainly two approaches for this. One of them is to identify each speaker using speaker diarization system and then count them. And the second one is to count the number of speakers directly. So with the first approaches, there are multiple drawbacks. The first one is that the diarization system needs the maximum number of speakers as a prior information, and usually they are more complex to be integrated into another backend speech technology system, such as an ASR system. However, if we count the number of speakers directly, we are able to build a simpler solution that can be easily integrated with other backend speech systems, and they can perform real-time pre-processing for estimating the number of active sources. As you can see here, the spectral magnitude or the spectral features of speech are affected by the presence of multiple speakers. In the top row, you can see the spectral magnitude for a single talker and multiple speakers speech signal, and then in the bottom you can see the pictogram for single talker and multiple talkers in speech. Pictogram is an enhanced version of a spectrogram that has been estimated by amplitude and frequency modulation analysis, which decomposes speech spectral subbands into amplitude and frequency components. So here we can see that by looking into the spectral features of speech, we can tell that there is an overlap speech, but it is hard to estimate the number of active speakers within that segment. Therefore, here we are proposing a convolutional neural network based system to detect the number of active sources. And our motivation for this project is to relax the assumption of many of the speech technology systems about the number of coherent sources in a speech segment. So as we can see, there are multiple speakers here in the scenario that the speech for each speaker has been added, and it creates the overlap speech. But if we zoom into these overlapping speech, we can see that in many segments of this audio, not all the speakers are active. So in some part of it, only one speaker is active, but in other parts of it, we have 2 or 3 active speakers. Therefore, it is very important to have a high resolution in detecting the number of active speakers. In this slide, you can see our proposed attention-guided CNN. We have a CNN network to extract higher level features based on the speech spectrum. And then once this higher level features have been extracted, they are summarized into a feature vector by using some sort of temporal aggregation. So the basic and conventional way to perform this temporal aggregation is to perform average pooling. However, this is not a very effective approach. Therefore, we propose to use attention mechanism to summarize the entire information that exists in the feature map into a feature vector. And then once we have the feature vector, we fed that into our fully connected classifier for the final decision. We have 4 classes at the output: non-speech, 1 speaker, 2 speaker, and 3 speaker. So the main focus is on the attention mechanism, which is the temporal aggregation that we perform to preserve the information that is crucial for detecting the number of speakers in the recording. So how attention mechanism works? Actually, attention is just performs an average pooling, but it finds some regions in the feature map that they contain more information, and the attention assigns higher weights to those regions. However, for doing so, attention needs query, key, and value to find those information-rich regions in the feature map and to calculate reasonable weights for those regions. So the query is a pattern that we aim to find in the feature map. The key is a representation for each time step to compare the query with, and the value is a representation for each time step that is returned by the attention mechanism. So if we compare the attention to Google search engine, we can clearly define each of these terms. So assume that like we have Google search engine with a very simple eyeglasses database. Each eyeglasses have been saved with a pair of key and value. And once a person is searching for a certain kind of eyeglasses, they put in a query. They type in a query. For example, in this case, the person is looking for oval eyeglasses. So what Google does is it takes the query, it compares the query with the key that it has for each element in the database, and if the similarity between key and query is high, then the search engine returns the value for that particular database. Particular data point in the database. So in this case, if we search for oval eyeglasses, Google returns the round eyeglasses because it has the highest similarity with the query. However, if we have a bad query, let's say tall eyeglasses, probably Google is not going to return anything because that query does not match any of the keys. So in our application, the query is a trainable vector, which the system learns through the training phase what to look for in the feature map. However, the key and the value are calculated by applying 2 independent fully connected layer and the feature map, estimated by which the feature map is the output of the convolutional neural network. And then the output of each fully connected layer is a matrix, which we call key and value. And the attention compares, in the attention mechanism, the query is compared with the key for each time step by performing the dot product between the query and key. And if the output of the dot product is high, it means that the similarity between key and the query is high. And we apply the softmax activation function to calculate a weight for that time step based on the amount of similarity that it has with the query. So once we have all the weights for each time step, we can multiply the weights and the time steps, and then we can average them across the time axis to summarize the entire feature map into a feature vector, which ensures that all the critical and crucial information have been preserved within the feature vector. So to evaluate our proposed system, we run several experiments on Wall Street Journal corpus, and we simulate the overlapping speech. We create over 20,000 overlapping speech for the training set, and our cross-validation and test set, they each have 2,000 examples. We use an 8-layer 2D convolutional neural network with kernel size of 5 by 5 and 128 channel size. And for the classifier, we use 2 fully connected layers, which each of them has 256 neurons. And then we use SGD optimizer with learning rate of 0.01. In the figures here, you can see the loss for training, the training loss and the cross-validation loss, and on the right you can see the accuracy for the train set and the cross-validation set. And as you can see, as the epochs are performed, the training and cross-validation loss decreases, and the fact that like the cross-validation loss is very close to the training loss manifests the generalization power of the network to the unseen examples, which is a very good sign because the network is able to perform well on the examples that it hasn't seen during the training. So for the evaluation metrics, we use accuracy, precision, recall, and F-score. We have 2 scenarios here. One of them is real-time processing, which we consider as like processing 20 frames of speech as input. And for the offline processing, we consider 100 frames. Just to mention that like 20 frames equals 0.2 second of audio, and 100 frames equals almost 1 second of audio in the input of the system. So in the table, in the top table, you can see the results for real-time processing on 20 frames input speech. And as you can see, attention outperforms the baseline, which is average pooling, by almost 3 to 5% in different metrics, accuracy, precision, and recall, and it achieves almost like 76% for all the metrics, which is a very good performance considered for a real-time application. However, for a 1 second input speech, the attention mechanisms performance exceeds 92%. Which is almost like 2 or 3% improvement compared to the average pooling. And in the figure, you can see that we have evaluated the performance of the attention mechanism and the average pooling for different input speech frames. And as you can see, attention outperforms the average pooling for all amount of input speech. In terms of accuracy, weighted accuracy, precision, and recall. So in this work, we addressed source counting by formulating a real-time attention-guided CNN network solution. The proposed method achieves 76% on real-time source counting scenario, 20 frames, which is almost 0.2 seconds of audio. The performance of attention-guided CNN exceeds 92% accuracy, precision, and recall for offline application, which is 100 frames, equal to 1 second of audio. And we also studied the effect of the proposed method on detecting non-speech frames, which eliminates the need for an SAD system. Please, for more information, refer to the paper, and do not hesitate to reach out to me if you have any question. Thank you very much for attending this presentation.